Yeah, thank you so much, Nikolai. Thank you so much, Maryam, for joining. We are very proud to have you today to tell us about irregular computations on sparse patterns. Yeah, with that, I would like you to get started without further ado, and Nikolai is going to introduce. Thank you.
Thank you.
Okay. Yep. Thank you, Torsten. And again, thank you, Maryam, for agreeing to come and present a talk. So Maryam is an assistant professor in the computer science department at the University of Toronto. And she is also the Canada Research Chair in Parallel and Distributed Computing. She was previously an assistant professor at Rutgers University, a postdoctoral researcher at MIT. She did her PhD at McGill University. And beyond her Canada Research Chair Award, she also has received the Ontario Early Researcher Award and the ACM SRC Grand Finale Prize. Without further ado, Maryam, please take it away.
Hi, everyone. Thanks for inviting me. So I'll get started. In this talk, I'm going to talk about inspecting irregular computation patterns to generate fast code. And this is specifically on sparse computations. And the research I'll talk about is what we do in our group Paramatics. So you can also visit our group page to get more information. Now, before I dive into the actual talk, I'm going to give you the general objective, research objective for our group, which is to build high-performance systems and solutions with the mission to actually work across the stack. So when we build systems, we believe that you can get fast code and high performance by understanding the application and the underlying numerical methods and optimization algorithms, so that when and if they need reformulations, you should do that, because sometimes they are inherently not scalable. And as a result of that, that kind of analysis also guides our changes to the algorithms to make them become parallel. Also, compilers and systems, when designed in isolation without information from the application, they typically only can optimize so much. So this is why we also work on building domain-specific compilers and systems that are tailored to the kinds of structures that you would see in a specific application. And as a result, they can give significantly better speedups compared to using like a general purpose approach in your compiler. And so in here, I've somewhat divided also, even though these are somewhat like connected together, our work based on the classes of things we do. So some of our work is, as I mentioned, on changing, for example, the optimization algorithms so that they're inherently better scalable. Or part of our work is building parallel algorithms, and very often they are somewhat guided by the actual domain and the numerical method. And at the other end of the spectrum, we build domain-specific compilers and code generations. Now, today I will talk about a line of work that's on doing sparsity-specific code specialization, and I'll point to two of these works specifically in more detail to tell you why it's important to understand the sparsity patterns to be able to better specialize and optimize code. So the work that I will talk about is Sympiler and NASOQ. Sympiler is where you look at sparsity patterns, and considering that they're static, you analyze them and you specialize and generate code. And in NASOQ, we look at when changes in the sparsity pattern are dynamic, how can you actually somewhat accommodate these kinds of changes and generate fast code. And so I'll first talk about Sympiler. And before I explain Sympiler through a running example, I'll just give a very quick background on linear systems of equations. To show you why sparsity is important and where do we usually come across these kinds of sparse computations. So in a lot of scientific problems, as you most probably already know, you end up solving a linear system of equations. And you can actually show that, for example, with AX equal to B. And A, which is, for example, your stiffness matrix, is typically sparse. Sparse meaning you have a very few non-zeros, and the rest of the matrix is 0. So these dark circles here will be your non-zeros. And if B was your vector of unknowns for your boundary conditions, constraints that you know, then X is what you want to solve for. Now, there's two other kinds of terminologies I want to talk about because I will routinely use that. So one is sparsity pattern. So in here, I'm showing you two matrices. Both of these are sparse. But as you see, their non-zeros are scattered in different ways. So in other words, their sparsity pattern is different. So, and the information about this sparsity pattern is what's referred to as symbolic information. Now, the first line of the reason actually we came up with Sympiler and somewhat what inspired this entire line of research was when we realized that sparsity patterns in a lot of applications are typically static through reasonable periods of time in your simulation. For example, if you're doing a computer graphics simulation or some sort of a CFD simulation, if you're not refining your mesh frequently, there's a good chance that your matrices in your solver will maintain the same sparsity pattern and the numerical values change. And also, for example, if you're solving some sort of a power flow simulation, your grid structure doesn't change often. What changes is the amount of power that you pump into the grid or you consume from it. So the Jacobians that you end up assembling, their sparsity also doesn't change very frequently in the Newton solvers that you use. So there's a lot of applications for this, and this is somewhat what we use as inspiration to build a Sympiler. So what Sympiler does is it's a domain-specific code generator that it actually analyzes the symbolic information of sparse computations and uses that to guide code transformations and to be able to generate highly specialized code. And ParSy, which is the follow-up to Sympiler, enables Sympiler to generate parallel code. So Sympiler vanilla does other compiler optimizations, and then ParSy comes and adds parallelism to it. Now, I'm going to use a somewhat simple running example to explain how Sympiler works, and that's literally all you need to know to understand what Sympiler does. So let's imagine you're trying to solve Lx equal to B. L is a lower triangular matrix, and it's sparse. B is your vector of knowns, and you want to solve for X. Now, if you B is also sparse in this example. And with that information, if you didn't know that X is also sparse, then you would have to solve for every value of X. For example, if you wanted to solve X1, you would visit the first column of L, you will take the non-zero in B, and then you will solve for X1, imagining L is in column search format. And then you would have to do that for every index. And if your matrix had a rank n and n was big, then you would have to, for example, do millions of iterations to find X. Now, if you knew a priori that X is also going to be sparse, then you could have done a better job in solving for X. If, for example, you knew that certain locations of X are going to be non-zero, you could just go and find those and compute for those. But so there is a theorem out there that gives you that information. The theorem says that if there is a non-zero in B, there's also going to be a non-zero, neglecting numerical cancellation, in X. And then every other element in X that you can reach through a current non-zero in X using the matrix L will also become a non-zero. So this theorem is called the Gilbert theorem. And just to explain it a bit more, let's imagine that B of J is a non-zero. So X of J is going to be a non-zero based on the first part of the theorem. And then we would know X of I is a non-zero if we can reach, if L of I, J, is also a non-zero, because in that case, we can reach X of I using X of J. So with this kind of reach, you can find out every single location that X is going to be a non-zero, And that's what's called as the Reachset. And to somewhat explain this in using the DAG, in here I'm showing you the DAG of computation for the triangular solve. You can see every node in this DAG as one column of L, or like one element of X or B, and the edges here show the flow of computation. And our objective in this exercise is to color every node in X that its corresponding in the graph, that its corresponding index in X is also going to be a non-zero. And so based on the first part of the theorem, because B1 and B6 are non-zero, 1 and 6 get colored. Now, as I mentioned, if you can do a reach into the matrix, you can see where else you will also have a non-zero. And this reach in the DAG is going to be just doing a depth first search. So through that search, we are able to realize that elements 1, 6, 7, 8, 9, and 10 in X are going to be a non-zero. So now we have a reach set. Now, if we pause for a second, what we did here up to now is we analyzed the sparsity pattern of the input matrix, and with the knowledge of the kinds of computation we were doing, we were able to extract some symbolic information, which is the reach set. Now, I'll tell you how this can be used to do code transformations. Let's go back and revisit the triangular solve kernel. As I mentioned, you have to do n iterations, n equal to the rank of the matrix, if you were not, if it wasn't optimized. And so this can be a very costly loop to execute. Now, with the symbolic information, if we were past the reach set, we could actually enable iteration pruning, which is a compiler optimization method, and prune the iteration space so that we're just doing 6 iterations. We're going through every single element in X that's going to be a non-zero, and we're going to populate that, and the rest are going to be 0. So the actual depth first search that we did in the DAG allowed us to enable prune optimization. Now, there's many other optimizations that you could do. For example, let's imagine that you look at the sparsity pattern and you say, there's certain iterations in my code that are taking longer, and I want to peel them off. So you can actually look at the columns and have a threshold, and that threshold will tell you, okay, let's peel off these specific columns because their sparsity pattern shows that they have X amount of non-zeros, and you can peel them off. So through these kinds of symbolic analysis, we also enabled loop peeling. So this is actually what Sympiler vanilla does. It actually looks at the sparsity patterns, and then it takes information from that. These are called symbolic information, and it would use that to guide compiler optimizations. And I'm not going to go into details of how Sympiler has changed to, for example, be able to do this inspection sometimes at compile time, sometimes at runtime, and even be able to accommodate dynamic sparsity patterns for certain scenarios. But that's the general idea. What I will show you here is the symbolic inspector module in Sympiler, just to give you an overview of how this is implemented in one implementation of Sympiler. So if you see here, for example, you can have some sort of a domain-specific language where the user says, well, here's my sparsity pattern, here's my numerical method. And then in Sympiler, we take these as inputs. And then at compile time, for example, we run the symbolic inspector. Then the inspector passes the information into the transformation modules. And then we generate a code, and that code gets executed. So if we focus, for example, in the symbolic inspector, as I mentioned, inside the symbolic inspector, we know the numerical method by now, and we also know the sparsity pattern. So we'll build the DAGs that we need to be able to do some sort of an inspection into the DAG. And a reminder on why this is useful, if you look at the sparse triangular solve, you see that there is an indirection. There's an indirect array access when you're accessing X in the last line of the code. This is where, when you throw this at a compiler, it won't optimize because there's indirection here. So what happens in Sympiler is we resolve this indirection. We actually give it the actual values of this access. And as a result, you can enable even more compiler optimizations beside the transformations that are domain specific or inspector guided. So in the symbolic inspection module, for example, if the input was a triangular solve, we'll build the DAG for that computation. As I showed you, for example, you run an inspection strategy that's able to create a Reachset, and that will guide prune optimizations in the transformation phase. Or another example is you can run a node equivalence on the graph, and that will tell you which of the columns in your matrix have the same sparsity patterns. So these are known as supernodes in sparse computations, and they're special because they have some sort of a blocked structure, and so you can enable blocking and cache optimizations for that. So this is another example of an inspection strategy that will enable some compiler optimization. Now, what ParSy does is it adds an extra inspection strategy to Sympiler, and that inspection strategy is an algorithm that's able to take a DAG and split it up in a way so you would have balanced workloads and enough of them to run on a parallel machine, and at the same time have good locality. And for example, here I'm also showing you that if the input algorithm was Cholesky factorization, it will build an elimination tree. An elimination tree, as I will discuss later on, captures the computation order in Cholesky factorization, the computation pattern in Cholesky factorization, and then you will run inspectors over this so you can generate sets to guide the code transformations. So this is somewhat, this line that I talked about tells you what Sympiler and ParSy do in their inspector, and then the transformations are more trivial. They're just compiler optimizations guided by the inspection information. Now, I'm briefly going to point out some example results that you can get out of this. So I'm going to show you results for a bunch of matrices from the Sweet Sparse matrix collection. And they come from different applications and different sizes. So in this graph, in the x-axis, we're showing the different matrices, and in the y-axis, we have gigafloating point operations per second. So the higher, the better. Here's Intel MKL for the triangular solve, and here's the performance you get out of ParSy if you were optimizing the triangular solve. Now, these are the executed code, the runtime of the generated code. Now, I'm also showing you something for Cholesky, the results for Cholesky. So the blue bar here is MKL Paradiso using the Metis reordering, and the other one is Pastix. And as you see, out of using ParSy and Sympiler, you can get decent speedups here. And what's important here is that the code is auto-generated here. We're not manually optimizing the code. We're able to beat libraries. And there's also many other low-level compiler optimizations that somewhat ParSy opens the space for to be applied, and we haven't explored that space. This is out of the inspector-guided transformations and the kinds of optimizations that we've applied up to now. And you might wonder what's the overhead of the inspector. So in here, I'm showing you the accumulated time of ParSy compared to the accumulated time of the libraries. And accumulated time meaning we add the inspection time as well as the actual code running, the numerical phase of the algorithm, the code. As you see, Sympiler is still beating the libraries, which it's not the same speed ups, but it's still beating them, which means that even if your sparsity patterns do change, you're still better off using this approach that Sympiler proposes. And yeah, so this is typically the idea. So even if your sparsity patterns change, there's ways to still use Sympiler because the inspection time It doesn't have huge overheads. Now, the other part, one thing that you might ask is, okay, what if my sparsity patterns change moderately? I don't have drastic changes in my sparsity pattern, because in that case, you don't really need to run the entire Sympiler inspection from scratch. There's ways to somewhat optimize your code so you can actually bring in those moderate changes into your code. And this is what leads me into the remaining part of the talk, which is NASOQ. So what I'm going to do in the remaining part of the talk is show you through an example, and the example is going to be quadratic programs. That in this specific example, you'll see that sparsity patterns incrementally change during the actual application. And as a result of that, I'll show you how the symbolic analysis kind of approach can make the solvers for QPs really fast. Now, QPs are very important. They're used in many different applications, and we do run it on different kinds of applications, as I will show you in the results. But this was specifically sent to SIGGRAPH because the graphics community, computer graphics community, are very interested in fast QP solvers. And so NASOQ is a numerically accurate, sparsity-oriented QP solver. It's faster and more accurate than competitive QP solvers out there. Now, before I dive into the actual how things work in NASOQ, I'll give you a quick overview and reminder of what QPs are. So in a quadratic program, when you're trying to solve an objective function, minimize it or maximize it, under certain constraints. So in here, you have a quadratic objective function, and you have equality and inequality constraints. So AX equal to B is your equality constraints, and CX smaller equal to D is a set of inequality constraints. You want to solve your quadratic objective function while satisfying these constraints. And so H here is your objective matrix, A is your equality matrix, and C is your inequality matrix. This is not easy to solve, and a typical standard approach is to satisfy the KKT conditions. These conditions, what they do is they solve the objective function, and at the same time will actually satisfy the constraints. I'll just briefly point to the first and the second one. So for example, primal feasibility, as you can see here, is trying to make sure that the constraints are satisfied, and they're going to be satisfied up to a specific error. Or the stationarity condition makes sure that you're going towards the right descent. X here is your primal solution, and Y and Z here are what's known as dual solutions or your Lagrangians. And so the other conditions also try to do the same thing. One of them is making sure your Lagrangians are going to be positive. So anyway, what's important here is, in NASOQ, what we do is we work with the KKT conditions, and we make sure that their error is below a threshold. And as far as that's satisfied, we've maintained accuracy. So now, the way you would solve and satisfy these KKT conditions is to solve a KKT system. So here I'm taking the KKT conditions and showing them in a matrix form. This is known as the KKT system. As you see here, H is your objective matrix. It came from your objective function. A in red is your equality constraint matrix, and C is your inequality constraint matrix. It holds the inequality constraints. I'm intentionally showing them in blue because we're going to use this color to understand how this affects sparsity changes when you're trying to solve the KKT system. Now, in the next slide, I'm going to show you why solving this system is expensive using, for example, the Goldfarb method, and how it relates to sparsity changes. So one of the more accurate solutions and ways to solve the KKT system is to use the Goldfarb-Idnani method. In the Goldfarb method, you have two phases. In the initialization phase, you take the KKT system, you remove you actually don't include the inequality constraints, but you add the matrix A here, which holds the equality constraints, and you have the objective matrix here, and you find an initial solution. Then in each iteration of an optimality phase, you add the inequality constraints. So you add the inequality constraint, you solve the system, you find the right descent, you update your solution, and you move to another inequality constraint. And every time an inequality constraint is added, it gets added to CW, which is your active set. And sometimes you can remove inequality constraints, but that's the general idea. Now, if you go and see, okay, how do we solve this system? One way, okay, the system in the feasibility phase there's a KKT matrix there, and a direct solution to this is to take the KKT matrix and factorize it. Matrix factorization by itself is a costly process, and I will talk about that. But what's important here is if you can factorize this matrix, you'll have the initial solution. Then inside the optimality phase, let's imagine in a specific iteration, you added a constraint. So you see now a row and a column that have blue dots have been added to the KKT matrix. So to solve the system in that iteration, you would have to do a matrix factorization for this KKT matrix. And as you progress, you're going to add more and more of these inequality constraints. And you can see here that your KKT matrix is changing. It's changing with the addition of the inequality constraints. And the standard typical approach is to refactorize the KKT matrix every time. And you can see from this that this is why this can have very large overheads and will be very poorly scalable. Even though the Goldfarb method is one of the more accurate techniques out there, it's not used by the community much. And the typical approach is to even use indirect methods to solve this system, and they will actually break down the sparsity pattern. So this kind of approach that you use a direct solver to solve these has its own overheads. It's because you need to refactorize things. But one thing that you might have realized is as we add constraints, the sparsity moderately changes. Things get added, but there's only a constraint or two being added or removed. And this is exactly what the NASOQ realizes, and as a result, optimizes its computations for. So NASOQ is a QP solver that's more accurate and it's faster than comparative QP solvers. It's more accurate primarily because of LBL, which is a new way, an efficient way of doing LDL factorization. I'm not going to talk about accuracy here. I'm mostly going to talk about why it's faster. And the reason is because it does symbolic analysis to enable fast factorizations. So to understand how NASOQ functions, I'll just do a quick reminder of matrix factorizations. When you're trying to, if you remember, I just said that in the Goldfarb method, you need to factorize the KKT matrix, and that by itself can be very expensive. So when you have a matrix A, for example, and you want to compute its factors, sometimes, like, for example, A can be equal to LL transpose, and you want to find L so it can allow you to solve the system that A is involved with. To just find this factor, you would have to go and compute each column of L one after another by touching columns in A. And what's interesting is during this computation, you typically introduce additional non-zeros into L. So the lower part of L will have a different sparsity pattern from that of A because of what's called as fill-ins. Now, fill-ins have caused, for example, two problems. One of it is they will add additional computations, and the other is they will make this factorization process be quite dynamic. So if you don't do anything a priori to figure out where you will have a fill-in, it's very hard to optimize the factorization process because the structure is dynamic. Now, there are good ways around that, most popular being having an elimination tree. So what an elimination tree does, it's a symbolic structure that tells you where you will have fill-in and what is the computation pattern of the factorization process. So in here, I'm showing you an elimination tree. I'm not showing edges, but this is directed actually. And so for example, if you want to compute the 6th column of L, from this tree, you can see that you would need columns 5, 3, 4, and 2. And you also would know where you would have a fill-in. And this is very standard practice in libraries, that they would actually build the elimination tree so it would guide their factorization and it would allow them to optimize the computations of the factorization. Now, with that information, I can now explain how NASOQ functions. So let's go back to the KKT matrix. Before doing anything with the Goldfarb method or adding or removing constraints, what we do in NASOQ is we take the objective matrix H as well as the A and C, which are equality and inequality constraints, and we add them all into a big matrix called the inclusive KKT matrix. We're only adding the non-zero patterns. We don't care about the numerical values because we're doing things symbolically here. And there's a lot of benefits to that. And what I should also note is that in all QP problems, you know all your constraints a priori. So with that information, you can build this inclusive matrix. And then we start playing with this inclusive matrix to help the upcoming computations. And there's a few small things we do. For example, we change and reorder the matrix in a way so that we have less fill-in. We also do reordering so that we have more supernodes. So as I mentioned, supernodes are good in sparse computations because they now enable, for example, for blocking. Another thing we do is we strategically distribute these blue columns. These are the inequality constraints between the supernodes. We try not to put two inequality constraints in the same supernode because not having them in the same supernode allows us to do certain optimizations during the Goldfarb method. So these are some of the optimizations that we can do by just having the inclusive KKT matrix. Not only that, just having the inclusive KKT matrix and building the inclusive L factor a priori symbolically, which also indirectly leads us to having an inclusive elimination tree, helps us to, in simple words, have placeholders for where the inequality constraints will come in. So now your data structures are not dynamic. You can statically allocate space for these. And not only that, as you will see, this kind of structure allows you to reuse pre-computed values of your L factor. So in here, the inclusive elimination tree has, so I'm removing all the, I'm making all the equality constraints that were in red before in the same color as the objective matrix because they're all black and we don't care about them. We care about how we add the inequality constraints because those were what were growing the KKT matrix in the Goldfarb method. So as you see here, these blue dots, these blue circles here are correspond to all the inequality constraints that we will eventually end up adding or removing during our QP solve. Now, if you go back to the Goldfarb method, in the feasibility phase, we don't have any inequality constraints. So we will just prune the elimination tree and use that to compute the L factor that I'm showing you down here. So we will fill up the numerical value for all of these dark circles, and that L factor will allow us to solve the system in the feasibility phase. And if you realize I used the word pruning, this actually is somewhat directly connected to how Sympiler prunes iteration spaces. So these can all lead to certain transformations that you can enable and have really fast code for this approach. Now, if we go inside the optimality phase, and let's imagine that we activated a constraint that's in node 7. through adding that, because we already have the skeleton, we actually just have to activate that node in the elimination tree structure, and then we exactly know where to populate in the L factor. So we go to supernode 7 in the L factor and populate the non-zeros there. Not only that, of course, adding a node into your elimination tree does affect other nodes, but because we have the elimination tree, we can track this down and we only change whoever gets affected. So all the dark dots here won't be changed. These are previously computed values of the L factor before this constraint was added, and they still haven't changed. So they can be reused, and the rest of the points do change because the constraint that we added does affect them. So as we see here, through this process, through symbolic analysis, we were able to track these incremental dynamic changes to the sparsity pattern, and as a result, enable really good optimizations and make the Goldfarb method, as you will see in the next coming slides, be runnable, and so be scalable in better terms. So I'm going to show you some results for this. Now, when we were actually working on the NASOQ work, we realized that there's no repository for sparse QPs. It was very hard. We had to actually knock at the doors of different practitioners and tell them, okay, can you give us a QP that's sparse and you care about and you want it to scale? And as a result of that, we actually built a repository that you can find in the NASOQ link that has 1,500 sparse QPs. These come from different applications, robotics, graphics, and for example, as you can see, a good amount of them are from contact simulation in computer graphics and so on. So you're also very welcome, and we will actually be very happy if you can contribute your sparse QPs into the repository. So we ran NASOQ and other QP solvers on this set of QPs that we solved. And here is the performance and speed up and the accuracy. So before I actually talk about this figure, I have to put another note here that I didn't have time to talk about. NASOQ has two versions. One version is a fixed version, and the other one is the tuned version. In the tuned version, you can actually go and tune 3 parameters we have. One of is, for example, the number of iterations in the iterative refinement, or its threshold. So you can tune that for your specific application and get really good accuracies for hard to solve QP problems. And from the 1,500 problems we solved, there were only 7 or 8 that NASOQ tune doesn't converge for. So NASOQ tune almost converges for everything in our QP suite that we have. And as you can see, even NASOQ fixed that requires no tuning converges for over 99% of the QP problems. While OSQP, Gurobi, and MOSEC don't have these kinds of convergences. Now, also, you can see that NASOQ fixed and NASOQ tuned are considerably faster than other solvers for QPs. So I hope I've convinced you that studying sparsity patterns is interesting. And if they're static or they're dynamic, you could still use that. You can do that kind of inspection, and you can actually specialize code. So Sympiler does that primarily for static sparsity patterns, and NASOQ does that for dynamic updates. We do have a line of work, and I'm going to quickly point to a few before I finish the talk. For example, in another work called MathRocks, what we did is in a lot of computations in machine learning and in physics simulation, you have hierarchical matrix structures. What does that mean? So let's imagine you have a point distribution and you want to apply a Gaussian kernel to that point distribution. For the points that are close in a neighborhood, they are highly coupled. And the points that are further from each other, they have loose coupling. Now, when you apply this kernel function to it, you will assemble a kernel matrix. That matrix is typically dense, but it's data sparse, meaning that the parts that relate to the far coupling have less information, so you can approximate them out. And this kind of data sparse structure is something that we investigate and we inspect in Matrox. So we go and our inspector at Matrox is actually split. Part of it runs at compile time and part of it runs at runtime. The part that runs on compile time looks at the point distribution, captures the data sparsity, and generates specialized code for that sparsity pattern. And the reason for that is a lot of the times a practitioner doesn't change the point distribution a lot, or at least they change in a way so that your hierarchical structure still can remain the same, but they frequently want to tune the accuracy of what they're solving for. And that tuning of the accuracy you can still do while using the same kind of analysis you did on the data sparsity. So we have inspectors at runtime that take in the accuracy at runtime and take in even the kernel function at runtime and can still use the generated code for that specific structure that came in. And so this is what Matrox does. We've also recently looked into, okay, what if you have multiple sparse kernels and then you want to run them at the same time? Can you look at the sparsity pattern jointly, and as a result of that, be able to do joint analysis of sparsity structures and then specialize code for them? So somewhat this enables for loop fusion in sparse computations. And finally, you might ask, okay, all of the inspectors you're talking about are written by you. These are not compiler generated, and these are like hard to write and all that. Is there anything we could do to have inspectors also be compiler generated? We're moving towards those. They're not smart inspectors yet, but you can read one of our papers that I'm showing you here, in which we make an effort. There's still some domain-specific information we give, but now we can generate these inspectors automatically to resolve dependencies. And so that's the direction that we are also looking into. And that concludes my talk. We'll be happy to answer questions.
Thank you, Maryam, for the excellent talk. Before we move to Q&A, I want to mention that we have our next SPCL BCast talk on the 6th of May at the same time, where Aparna Chandramulawasharan from UC Irvine will be speaking.